All right, so in this video, let's actually go over the nuts and the bolts of using trig sub. So we're going to do the trig substitution for this integral that's up here, x over square root of x squared plus 1. Now, I know in the previous video we went through the substitution, so let's just remind ourselves of the process for that. We looked at what's underneath the square root, that x squared plus 1 term, and that x squared plus 1, the way in which I sort of look at this is I say, okay, where's the x term? Well, the x term looks like there, so we can replace that with open parentheses, and then we just have this plus 1 tacked on. And what I'm actually looking for is which trig identity out of those Pythagorean identities to help us out. So let's just go back and remember what some of those identities were. These were those following identities. Cosine squared is 1 minus sine squared. Secant squared is 1 plus tangent squared. And tangent squared is secant squared minus 1. So what we're actually trying to do in this case is match what identity has that kind of skeletal form, if you will, something squared plus 1, on the right-hand side of those identities. And well, we can go through the first case. We have a 1 minus sine squared in that first cosine squared identity. So it doesn't look like that identity will work. In the second identity, the right-hand side, well, we have 1 plus something squared, which is the same thing as something squared plus 1. So this looks plausible. And again, if we check that last identity, tangent squared is secant squared minus 1. Well, that would be like parentheses squared minus 1, which doesn't look like it would be the case. So it looks like the identity we want is this second one. So this is what I mean by try to recognize which substitution we think we're going to make. So in this case, what we need to do is, like we said in the previous video, what we ideally want is a tangent squared for where we had that x squared term. So what that will necessitate in the first part is, well, recognizing which identity to make, which we just did. So this is again going with kind of the 3 parts of trig sub. We actually get to perform that substitution. And what we want to do is let x equal, in this case, tangent of theta. So anywhere there's an x in that original integral, we get to now replace with a tangent of theta. But the thing I want us to notice is we're working in terms of a theta variable now. This theta variable isn't the original integration variable we began with, that x. So we also, at this point, we get to do a change of variables that involves a dx into a d theta. And the way in which we do that is we take the derivative, just like we did for use substitution. So taking the derivative of x, which is tangent of theta, so taking the derivative of tangent of theta with respect to theta, that gives us a secant squared term. And what we want to do is substitute dx, or substitute our dx for something in terms of d theta. So from this line, what we can do is solve for dx in terms of d theta by cross multiplying and getting dx is equal to secant squared theta d theta. So we're going to get to use both of these substitutions into the above integral. And I just want to point out that when we did use substitution, we had to kind of divide by stuff to get dx in terms of du. Here, we're just cross multiplying that d theta over onto the other side. So let's go ahead and substitute those into the original integral. So substituting in what we have now for x, we have that tangent in place for x, which means in that square root in the denominator, we have a tangent squared inside plus 1. But we're not done yet because, well, we need to replace that dx that we had up above. So we're replacing dx with what we just found in terms of that relationship between dx d theta. That gives us a secant squared theta d theta. And that is what I mean by actually performing the substitution, not just substituting the trig function wherever we have an x, but we also have to do the dx to d theta swap by taking the derivative of that x equals whatever trig function we have. So we can try to clean this up just a little bit. So we have a tangent theta in the numerator. We're multiplying the whole thing by secant squared, so that's times secant squared theta. And then we're dividing by, well, square root of a tangent squared plus 1. And that is in terms of d theta. And we're not done yet because, well, this doesn't look like it's really helped us out at all. We still have that square root there. But what I want us to pick up on is, what do we actually know tangent squared plus 1 is? This is where the whole purpose of trig substitution comes to play. If we go back to our identities up above, we know that, well, 1 plus tangent squared or tangent squared plus 1 is equal to a secant squared. So we can go ahead and substitute in that secant squared for what is inside that square root down below. So our integral then becomes the integral of, well, stuff upstairs, that tangent times secant squared term, except what's in that denominator now is just a secant squared d theta. And well, if we take the square root of something squared, that just gives us the thing back. So in this case, what this becomes is, well, tangent up above, a secant squared down below, and then we have a secant squared square rooted. So what's sitting there in the denominator now is, well, just a secant. And we can do a little bit of cancellation off once we put our d theta on there. We have a secant theta downstairs. We have a secant squared upstairs. So that just cancels out to give us one factor of secant in the numerator. So the overall integral we're looking at is the integral now of tangent theta times secant theta d theta. And that is finishing that first act, recognizing what substitution to make and actually performing that substitution. Which brings us now to part 2. And part 2 for us is computing the resulting trig integral. So what we just found was, well, we replaced all the x's with trig functions. So our whole integral now should be in terms of trig functions. And this is sort of where some of these problems get a bit messy. For us, this example is just to show you the different parts of trig sub. So actually, if we recognize this integral, we can just change the order of secant and tangent in the integrand. And that's an integral we automatically know the antiderivative of. The antiderivative being a secant theta. So performing the trig integral here is actually very straightforward. But again, I just want to emphasize, at this junction for solving the trig integrals, this is where we have to employ some of those other trig identities we just used in the preceding section, or we might have to play around with some of these integrals a little bit to try and compute their antiderivatives. For us at this stage, we had a trig integral, we were able to compute it, which brings us now to Act 3. Act 3 being converting back to the original integration variable. And I just want to point out here, this is in terms of theta. We need in terms of x. And the reason we need the antiderivative in terms of x is simply because our original integral that we started with is in terms of x. So the question becomes, how do we go back to the original variables? And this is where we get to use our knowledge of right triangles. So some bits for us to remember. was, if we remember all the way at the beginning, the substitution that we made was we let x equal tangent of theta. So another way to write this is, well, tangent of theta equals x over 1. And the reason I'm going for this kind of notation in looking at what tangent of theta is in terms of x is because that's going to be very useful for going back to the original variables. The only other thing we get to do now is, well, we get to start drawing some right triangles. And if you remember from back when you learned about trigonometry, we learned that tangent is equal to opposite over adjacent side. So when our right triangle below, if we define our angle theta to be the angle over there, we know that, well, the side next to that angle is adjacent, the side opposite is the opposite, and then the side on the hypotenuse, well, that's the hypotenuse side. So what we know from our original trig substitution that we did was tangent of theta equals x over 1. So in this case, what that means is, well, opposite is equal to x. And then the adjacent side is equal to 1. So really what I'm saying here is, of course, we have those trig identities, hypotenuse, opposite, adjacent, but we really just need those to fill out the sides of our triangle from our original substitution. So I'm just going to get rid of adjacent, opposite, and all of that to just tell us where those sides are. So we had that x was the opposite side and the adjacent side was 1, because we know that tangent is just equal to x over 1 or opposite over adjacent. And then through Pythagorean theorem, we know that the resulting side must be opposite squared plus adjacent squared, or x squared plus 1 squared, or x squared plus 1 under the square root. So the reason why we needed to make that triangle was, if you remember up above, our antiderivative was this secant theta plus c. So what we need to do is turn secant theta in terms of x. And the way in which we're going to do that is just notice that, well, secant of theta, if you remember, is equal to, well, 1 over cosine of theta. Cosine, of course, is adjacent over hypotenuse, which makes secant hypotenuse over adjacent. And we can just read the sides off that right triangle now. So if we look at the hypotenuse, that gives us the x squared plus 1. And then if we look at the adjacent side, well, that just gives us a 1. So at the end of the day here, what we actually get to do is write our final answer as, well, we know that secant theta plus c was our original antiderivative. Once we plug in what we know coming from that triangle, we get that this is the square root of x squared plus 1 all over 1. You don't actually need that 1 there. I'm just doing this for clarity, plus c. And that would be our final answer.